Work. Okay, perfect. Okay,
Yeah.
cool. Yeah, so welcome to the first MCRN AIM Community Colloquium. Really excited to be kicking this off, and I'm really excited to have our first speaker, Hans Kaper, who many of you know from Georgetown University, and many of you have read a book he's written, of course.
With the other Hans.
Right, with the other Hans, yeah, exactly.
I guess that's Hans's iPhone. He
Right.
doesn't show up.
Oh yeah, I see that now. Yeah. So yeah, very, very happy to be able to do this. And maybe just before we get started, I hinted in the emails I was sending out that we make small announcements about some funding opportunities that we'll have through the community. So we're intending to have people be able to apply for funds for things like travel for collaboration, offset cost of childcare, or equipment to facilitate remote collaboration, things like this. So we'll send out information on that fairly shortly here, how that will go. But we're certainly looking for ideas of things that you think money might be useful for. We'll also want a committee. So if anybody wants to volunteer to be on such a committee, please shoot me or Caitlin or Kate or James an email with any of those ideas, or if you want to volunteer to be on the committee. And we'll send out some of that information soon, which hopefully will be allow us to really support the community in a nice way. So then, other than that, let's see, very happy to have Hans here. He's going to be talking about the dynamics of glacial cycles. And so with that, I'll turn it over to you and we'll get going.
Okay. So, now where do I find my screen? Oh, here. Share. Okay. Can everybody see my title?
Mm-hmm.
Good. So thank you, Christian, and thank you, Emmanuel, for organizing this series. I'm impressed that you've already lined up speakers until January, and I'm particularly honored that I'll be the inaugural speaker of this series. I hope it will last a long time and that we all learn a lot. So my talk is titled Dynamics of Glacial Cycles. Apologies to, I think, Chris, who was the only one who has heard this talk last month in Leiden. It's a slight variation, but otherwise it's the same talk. So this is joint work that I've been doing over the last few years with Hans Engler, my colleague at Georgetown, Tasso, my son, and Theodore Vaux, who was a postdoc with Tasso at Boston University. Okay, if you want to read about this talk, I recommend that you, well, wait till next year. We're working on a second revised edition of the book Mathematics and Climate that will be issued again by SciM, probably towards the end of next year. There are two articles that I can refer to at the moment, an article from 2019 and another article from 2017. It shows that we've been working on this for a long time. It's a difficult problem in many ways, and it leads to many new problems, which is, I find it exciting. Okay, so here's the outline. I'll give you some background of the talk. What are glacial cycles? I'll briefly touch on Milankovitch's theory, which was developed in the 20s, 100 years ago. There are some issues that remain after Milankovitch's theory was published in the 1940s. Primarily what happened in the Pleistocene, in the transition from early to late Pleistocene, the so-called mid-Pleistocene transition. And the model that we'll be using is a model developed published in 1990 by Maasch and Saltzman. Saltzman was at MIT, was a colleague of Lorentz. The two of them published together. Maasch was, my guess, was a postdoc at Saltzman, in Saltzman's group. There are 4 items that I want to touch on. One is the key insight that Saltzman provided. the dynamical system that he set up, a 3D dynamical system. The reduced model that we used mostly, which is a two-dimensional model, and the bifurcation analysis that was done on the 2D and also 3D, but I'll discuss mostly the 2D dynamics, and then draw some conclusions. Okay, here is the temperature record going back 5.5 million years. BP stands for before present. So 5.5 million years before present. We start out on the left, which is something you have to remember. Geoscientists often let time run in the wrong direction. So here time runs forward from left to right. So 5.5 million years before the present, and here is the present on the right. Up until about 2.6 million years ago, it was a fairly steady situation. What I plot here are anomalies. So there is an average baseline that we use, which is marked 0, and you're a little slowly decreasing, but essentially staying constant until 6 million years ago. Then something happened, and you can see it started to cycle in a steady way with a cycle of 41,000 years. Then around a million years ago, plus or minus 200,000, things changed. You can tell something is happening in this area here, and cyclic phenomenon. This is a 100-year cycle, which has persisted over the last 400,000 years. So you can, I'll show a slide in more detail. You can clearly distinguish 4 cycles over this period. So this is called, this here, the 41,000 cycle is characteristic for the early Pleistocene. Then there's a mid-Pleistocene transition. And after that, you get the late Pleistocene, where the oscillatory behavior is different. And the cycle has changed 41,000. So where did this happen? There were people around, as far as we know. So no carbon was emitted by humans like today. Why did it change? And that's been a question that the geosciences community has been considered for quite a while. The first person really to come up with a theory was Milankovitch. Milankovitch was a geoscientist, but very mathematically oriented. So he saw that, he realized that, first of all, Earth's climate system is driven by what comes from the sun, solar radiation. The technical term is incident solar radiation, also abbreviated insolation, not insulation, but insolation, okay? Now, insolation varies as the Earth moves around the sun along its orbit, which is not circular, but elliptical. So there is an eccentricity. It is not, the orientation of the Earth is such that it is not the rotation axis, this dashed line here, is not the real one. The real one is tilted, and the tilt is called obliquity, denoted by T. And then there is a wobbly motion around this axis that is called precession. So these 3, eccentricity, tilt, and precession, sort of determine where the Earth is along its orbit around the sun. Now, the equations that govern this motion are well known. These are Kepler equations and modifications thereof. So you can take the celestial mechanics equations and integrate them over time and do this for the whole solar system. Not in the early days, of course, in the days of Milankovitch, it was the sun, the moon. Now, people are able to simulate the entire solar system, including 9 planets, so including Pluto, and generate time series for each of these parameters. So this is purely a computational job that's done by Lascar and this group in Paris. You can find the eccentricity, tilt, and precession over the course of as long as you want to go back, essentially. And if you do that, you see that eccentricity is a periodic phenomenon. It changes periodically with a period of 100,000 years and a longer period over 400,000 years. Obliquity, likewise, has a fairly fixed period of 41,000 years, and the precession roughly 29,000 years. It's a bit plus or minus. It's really, there are two cycles that are very close together. So these are given, right? We can compute them to our heart's content, and then on Earth relative to the sun at any time. And that's what Milankovitch realized. The quantity he considered was called Q65. So that was the average daily insolation in July, the month of July, averaged over the month of July, at 65 degrees north. Now, why did he take 65 degrees north? It's a little below the Arctic Circle. That's where the land mass dominates the ocean. So he wanted to primarily focus on the land, the effect of land, and that's why he took 65 degrees north. And so, as I said, you can calculate the orbital parameters, which was done by Lascar most recently, 2004. Last publication was 2011. They're published on the web. You can use them, download them, and play with them to find all the interesting things. Now, there's another way to check this. This is computationally, so theoretically, mathematically, if you wish. But you can also look at proxies for the temperature, in particular sediment data. Sediments are the leftovers of critters that live in the ocean, or lakes, lake beds primarily here. And they have been studied in great detail since, well, the last 40, 50 years. The most recent and the most complete set is due to Lisicki and Remo, 2005. You can find all the data on the web and do them and play with them. It's a nice student project, actually. So you have two sources. One is computationally, based on the equations of celestial mechanics, and one is experimentally from lake bed data, sediment data. And you can analyze the power spectrum. You can do that over a period of 1 million years, let's say, 2 million years to 1 million years before the present, and then the next 1 million years, 1 million years before present to today. And then compare what you get here and what you get there. And you can see that the 41,000 year cycle of the early Pleistocene is essentially due to external forcing because of obliquity. Obliquity, you recall, has this 41,000 year cycle in it. It's the only one that is firmly fixed. And if you do a power spectrum analysis and compare, it's very consistent. So almost every geoscientist will tell you, yes, this is due to obliquity forcing. So it's an external force. However, the Milankovitch theory does not have an immediate explanation for the 100,000 year cycles of the late Pleistocene. There are arguments that are being made that, well, this is 100,000 year cycle comes because of eccentricity, but the signal is too weak to explain what you observe experimentally. So it really doesn't explain what happened. And it doesn't, there's no way to explain the mid-Pleistocene transition. The Milankovitch theory is just a continuous theory. Nothing changes, right? So what is the research challenge? Well, the question that Saltzman addressed was, can we now develop a conceptual model that can explain these two missing links? The late Pleistocene cycle of 100,000 years. This is called the 100,000 year problem in geoscience. And can we explain the mid-Pleistocene transition? So the question is really, can we develop a conceptual model? There's probably more than one, but a model that explains this. We are not going to predict it. We are going to explain what has been observed. Okay, so what did Saltzman observe? Well, he made two key observations. First of all, he noticed that there's a very strong correlation between temperature and atmospheric CO2 concentration. So you here in blue, you see the average, the global average temperature over the last 400,000 years. And in red is the change in the atmospheric CO2. And you can see there are 1, 2, 3, 4 periods, clearly. So that's a 100,000 year cycle, roughly, right? All these data come from Vostok ice core data, which is fairly reliable record, 422,000 years long. Okay, so that was one observation. So he suggested that maybe temperature and atmospheric CO2 are intimately connected. Somehow there may be a feedback mechanism that reinforces the 100,000 year cycle. And that mechanism is atmospheric CO2. That was one observation. The next observation he made was, well, okay, if atmospheric CO2 is important, what happens to it? So you have to look at the interplay between the ocean and the atmosphere. Atmospheric CO2 comes from ocean water. So let's study ocean dynamics. Ocean dynamics is driven by two things, temperature and salinity. So the ocean current around the globe is called thermohaline circulation, THC. It's also called the Great Conveyor Belt. Why? Well, look at the diagram here, which is a schematic. It's not real, it's a schematic, just to explain how water flows around the globe. Let's start at Antarctica, where it's cold. There's a permanent westerly wind blowing to the east. A westerly wind means it comes from the west, it goes to the east. The water flows into the Indian Ocean, into the Pacific, approaches the equator, warms up in the process, and when it warms up, it wells up. So red means it's warm, blue or purple is it's cold. So it sort of turns around and then gets driven through the Indonesian archipelago into the Indian Ocean. It flows around South Africa, goes up the Atlantic. This is all still warm because it gained a lot of heat on this trajectory, right? And then it comes in the Northern Atlantic, and look at what happens. It cools off because it's moving towards the pole and gets saltier. It takes up more salt, and therefore it sinks. This is the overturning circulation. This here. So coming from the equator, equatorial region, going back to the equatorial region after flipping somewhere between Norway and Greenland. It's a sketch, so don't take it too literally. This, for example, the Gulf Stream is part of this red arrow here, this red band here. And then, so it goes back to the Southern Atlantic and arrives again at Antarctica, and that is the cycle. It's called the Great Conveyor Belt. And you may ask, well, how long does it take to travel that long? It takes about 1,000 years. So this is a scale that's very different from the atmosphere scale. The atmosphere changes in a week or a month. The ocean changes in the course of 1,000 years. But the critical point is this. Remember, the glacial cycles were primarily concentrated in the Northern Hemisphere. So let's look what happened in the Northern Hemisphere. Warm water comes up here, it gets colder, gets heavier, sinks, and flows back. And at this point, it takes up a lot of atmospheric CO2. So this is sort of the nexus of this conveyor belt. If we want to explain how CO2 happens, how CO2 moves from the ocean to the atmosphere or vice versa, we have to study the North Atlantic deep water. That was Saltzman's second observation. So he came up with a model. Here we go. The paper that he published was 1990, Journal of Geophysical Research. As I said, joint work with Maasch. Maasch was one of his postdocs. He had other postdocs with whom he also published. So there's sort of a sequence of models that Saltzman developed in the 80s. And this is, in fact, there is a model after this one, which we have not studied. I'll not discuss that in detail. But there are several models which were published in the 80s, and the one in 1990 to us seemed like the most relevant, the most interesting. So it's formulated in 3 variables. I don't give you all the details how you get to this model, but believe me, it can be done. You have to work with the anomalies, so deviations from average, long-time averages. You have to make the problem dimensionless, and then you have to rescale some variables and parameters. You get 3 unknowns, x, y, and z in mathematical terms. X, think of it as the total global ice mass. So as you have a glacial cycle, it varies up and down. Y is the atmospheric CO2 concentration, which is intimately connected to temperature. And the third is this North Atlantic deep water, Z. And here are the equations. So x dot changes, it equilibrates, so there's a negative x, and it atmosphere. Consider Z first, this is North Atlantic. It integrates with a time scale Q, and it also is affected by the global ice mass. Now, these are both linear, very simple. Y is the critical one, and that's Saltzman's contribution, really. Y has changes because, well, first there's an internal change, and then there's an external effect due to North Atlantic deep water. And this is how I write it. He wrote it slightly differently, but you can see it's a very simple problem. S is a sort of a spoiler because S makes it asymmetrical. So Saltzman knew that the glacial cycles were not symmetric. It's not a fully symmetric motion. There is the freezing takes longer than the thaw. Represented that by the factor S. So S is sort of a spoiler because otherwise it's a nicely symmetric problem. If you change x, y, and z to negative x, negative y, negative z, everything is the same except this term. So it's a bit of a spoiler, but maybe it gives us an extra degree of freedom. What happens if S is 0? Then it's a simple, relatively simple problem. So you can play with these things. Now, what is Q? Q is just a scaling factor. It's a time scale. Here is a 1, here is a Q. So it's a ratio of the rate of change for the global ice mass and the North Atlantic deep water. Physicists tell you it has to, geoscientists tell you it has to be greater than 1. The others, P, Q, R, and S, are all positive. All right, well, that's a hint. Q is greater than 1. First of all, let me show you what Maasch and Saltzman found. They had this system of equations sorted by reverse engineering. Lo and behold, they found this periodic motion. Here is the global ice mass. It gets warmer, it gets colder, it gets colder, it gets warm, and colder, it gets warmer. Here is the atmospheric CO2. It's sort of out of phase, but you can see there are 4 peaks, 4 periods. And the Atlantic deep water, well, compare this to the top one. X plus Z is almost 0. That's a hint. All right, so this is their finding. So they did this by just computing, solving the system numerically. And they fixed the values. P is 1, Q is 1.2. Remember, Q has to be greater than 1. R is 0.8, S is 0.8. And U, this was an external forcing term that they included in their model, is 0. So there's no forcing. It's purely internal dynamics. Okay. Now, here we are. P, Q, R, and S, all positive, Q greater than 1. What does a mathematician do when you see this? You say, oh, Q greater than 1, 1.2, I'll make it 1.8, which is very large, right? Q much greater than 1. And see what happens. So you call epsilon 1 over Q, and your system becomes a slow, fast system. The first two equations don't get affected at all. But the third one gets an epsilon in front. Remember, it had a Q here in front. Q is 1 over epsilon, so you bring the epsilon to the other side. This is a slow, fast system. X and Y are slow, Z is fast, because in order to make this order 1, Z dot must be very large to compensate for the epsilon. So it's a very fast variable. In other words, the North Atlantic overturning circulation acts on a much shorter time scale than the ice mass. Of course, the next step is, well, what happens if epsilon is 0? This vanishes, arguing formally at this point. So x plus z must be 0, or close to 0, which we saw in the numerics, right? So let's take that. Let's take z equal minus x, substitute it in this second equation. The first equation is independent of z, so here we are. P of x comes from here, p negative z, r minus x squared y, plus s x squared. So you see, this is the oddball term. But we have reduced the dimension from a 3D system to a 2D system. And we can handle it very easily. So here it is again. You look for equilibrium states. Of course, the trivial state is always one solution. The trivial state, xy equals 0. And if r is greater than p, you find two other states. One is what is called the cold state, and the other is the warm state. And they are sort of located on the diagonal in the xy space. X star, which is the coordinate, the value of the x coordinate here is square root r minus p, so that tells you r must be greater than p. So these two extra states originate on the diagonal r is p. Note, so I've set s equals 0, right? I told you. You first make it as simple as possible. So s is 0, the spoiler is gone. And let's see what happens. Here is a bifurcation diagram. My trivial state is stable in O, in this region O, marked O, under this diagonal and this horizontal line. And on the line, the system becomes unstable due to a supercritical Hopf bifurcation. So as you cross this line, periodic solutions will be generated. The frequency depends on how far you are from this point. So the frequency increases as I move to the right. And then they grow and grow as you go up. So let's keep that in mind. The other two are stable in this region, marked Roman 3. They become unstable as you move to the right and cross this line. It's a subcritical Hopf bifurcation. On this diagonal here, well, there's a transition of exchange of stability between the trivial state and the warm and cold states. So this is a transcritical bifurcation, which is not very interesting, but it's there. Now, the interesting thing is here. The point 1, P is 1, R is 1. That's where two bifurcation curves get together. And that means interesting things can happen. This is a so-called Bogdanov-Tarkin singularity. It is the organizing center for the dynamics. All bifurcation curves must come out of this point. And if you zoom in at that point, which I will not discuss in detail, if you zoom in at that point, you see that the system is a perturbed Hamiltonian system. So there is a theory for such systems called the Melnikov theory that tells you how to find bifurcation, global bifurcation curves. Now I bring back the S. So what does the S breaks the symmetry, as I told you earlier. So what does that mean? Well, your trivial state is unaffected, which is you might have expected. The other two states, they are affected. First of all, R must be not just greater than P, but greater than P minus a quarter S squared. So this is sort of the shifted diagonal, right? R equals P minus a quarter X squared is the shift. The diagonal is just shifted a little below. You find a cold state again and a warm state. X is now X1 star, and you see there is the S and there is the S. If S is 0, it just reduces to square root R minus P, as before. Now, this has a plus sign and this has a minus sign. And that explains the word warm and the word cold. Cold means well, it means it's colder than average, right? And warmer than average. So the saddle node bifurcation, which generates these two states, happens on this shifted diagonal. Now we can draw the bifurcation diagram. So mind you, remember, for s equals 0, we had the diagonal, which is this upper line here, and then it disappears. But the shifted diagonal takes its place as the shifted diagonal. We had a horizontal line starting here, going going east. We still have it. We had a vertical line going north, and that splits into a parabola. Here, the left branch, here, the right branch. And there's a little gap in between. Because the point Q, where these two lines met for s equals 0, is now, that point has been split. There are now two singular points where the bifurcation curves meet, like here. The parabola meets the horizontal line. Here, the parabola meets the shifted diagonal. So instead of one, we now have two Bogdanov-Takens points. The vertical line has opened up and become a parabola. This one is still the same. So P0, which was stable here below, is still stable below this line and to the right of this line. Supercritical half bifurcation as it crosses this horizontal line. And this is the cradle of periodic motions. As you move across, the system that used to be stable becomes unstable due to the half bifurcation. So periodic solutions are generated on this line, and then they move up and grow as you go. And the frequency depends on the distance from this point. So the frequency increases as you go to the right and then move up. All right, the other one, P1 and P2, P1 is sort of the cold state, and it's the uninteresting state. It's only stable in this region here, to the left of the left branch of the parabola. The other one, the warm state, which is the interesting state, is stable all the way up to the right branch of the parabola. So that has a much larger domain of stability. But on the line, it undergoes a subcritical half bifurcation. And there's even more happening. It's subcritical to begin with, and it can become supercritical above a certain point. So that's quite a delicate issue here. Anyway, the point is we have these two organizing centers. Every bifurcation curve originates either here or here. Let's take a look. We blow it up. You see what's happening. This is Q0, and the other one is here, Q1. This is the old line, the stability boundary for the cold state. This is the half bifurcation for the stable state, right? You come from below, it becomes unstable here. This red line is the stability boundary for the warm state. But there are many more in between. These blue dashed line, and the blue solid line, and the black solid line all represent bifurcation curves, global bifurcation. Saddle node bifurcations or limit cycles are they. Here are more details. You can see how complicated things become. Now, this gives us a way to analyze what happened in the Pleistocene. Let's take a dynamic point of view, and let's assume that one of the parameters, or two, we have P and R, right? P is horizontal here, R is vertical. Let's assume that one of them changes on a very, very slow time scale. I take P as an example. P is this one here. So I have a green line, I hope you can see it, starting here and changing slowly to the right. So I move P from 1.3 to 1.7. And the rate of change is very slow. I choose the rate of change to be 1 times 10 to the minus 3 per unit of time. And my unit of time is 10,000 years. So that means 1/100th of 1% per 1,000 years, which is roughly the speed of geologic change. Okay, let's see what happens. Same picture. I start out on the left and move to the right. And as I move, I cross various bifurcation curves. This is a saddle node bifurcation of limit cycles, which doesn't play a real role at this point, but later on. But then I hit that boundary for the stability of the warm state. Everything here is fine. The warm state is very stable. Think of the early Pleistocene, or what precedes it even. Here, things become unstable. So, what does an unstable state do? An unstable system do? It looks for a stable equilibrium. So as it moves across this line E2, it must find a new equilibrium. This is the mid-Pleistocene transition. It is searching for a new equilibrium. Now, once it has crossed the line, what happens? There are many candidate equilibrium states in this region here. Because they all originate here, I told you earlier, this is the stable trivial state, becomes unstable, it spawns periodic motion. These periodic cycles grow as you grow up here. They're stable, and they sit up here in waiting, so to speak. So mind you, it has nothing to do with where we came from. We came from here, but I told you they come from these limit cycles come from here. So it has nothing to do with what happened here. Nothing, it's not related to P2, and it has nothing to do with external forcing. It's simply an internal phenomenon. Things that become unstable here, no external forcing, and they keep wandering around, and I'll show you in the next picture where they go. Here is a detailed shot of what kind of periodic phenomena you can expect. So we've crossed this red line, and I told you the frequency goes up as I move to the right. That means that the period goes down as I move to the right. So they originate here, for example, with a period of 80,000 years, and it meanders and then disappears somehow here. And here it's a little less, 70 years, here's 60 years. Here's a 100-year cycle. Originates here, tiny, 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 you can't even see it. But then it moves, and as I cross these lines, in particular the red line, it hits on a 100,000-year cycle, on this curve. You can barely tell because everything happens in a very short scale. But as you cross the red line, things become unstable, and then it has to meet one of those isoperiod curves. And where it lands depends on the domain of attraction. So, repeating, there are many candidate states for equilibrium. These are all large amplitude stable limit cycles which originated on E0, this red line here, which is a little tilted. The period, well, you can start out with a 100,000-year cycle. You can move down to a 70, 90,000, 70,000 year cycle. But most likely, the first one that gets hit must be in the area of 100,000 years. Each of these stable limit cycles has its own basin of attraction. And wherever the periodic solution that was unstable, that came from P2, wherever it happens to fall into the basin of attraction, that's the new equilibrium state. So after this motion, and here I have drawn another arrow with a track that, again, well, in this case, it changes both P and R, but you can clearly see that somewhere, once it hits the red line, it must stay, it drops into the basin of attraction of one of these large amplitude stable limit cycles. So under the right scenario, we can arrive at limit cycles with the right period. That's the story. Again, I set out to design a model that could explain what happens. I don't say that it happened that way, but it is one possible mechanism to explain the mid-Pleistocene transition as well as the eventual 100,000 year cycle. And I would say, I leave it to you to work on this problem further. There are many more questions that we still have and like to ask. Thank you.
Okay, thank you so much, Hans. That was a wonderful talk. Definitely enjoyed that. And we certainly have time for some questions if anybody has one. Please feel free to just unmute and ask away.
I have a question for Hans.
Okay.
In your bifurcation diagram, right? So you have a half bifurcation, a transcritical bifurcation, and a Bogdanov-Tachan bifurcation. So each of them has a physical meaning, right? So I'm assuming the half bifurcation, when you have this birth, the supercritical one, when you have the birth of a limit cycle, right? So basically, you probably have the periodic motion that happens, but this is in the XY coordinates, right? So I'm looking at the global ice mass and the atmospheric CO2. Is that correct?
Yes, that's correct.
Okay. So then what is the meaning for the transcritical and the Bogdanov-Tachan? And because you're looking at the slow manifold, like I'm talking about the physical meaning, and because you're looking at the dynamics on the slow manifold, do we care about the North Atlantic deep water? Do we care about these variables?
Yes, because the North Atlantic deep water is always coupled to the ice. So x plus z equals 0. So I'm on the slow manifold, z is negative x. So you cannot just speak about x and y. Z is part of the game.
Yes, that's correct.
Does that answer your question? Or?
Well, I wanted to know further about the physical meaning for the transcritical and the Bogdanov-Tachan bifurcation.
Well, that's something I can't answer offhand, I must admit. Basically, you're asking what is the meaning of these two parameters P and R, right? Because the Bogdanov-Tachan's point is where both happen to be 1 or slightly off if S is positive. It is, let me say, we got to these parameters P and R by various substitutions and transformations. And in the end, it mixes all sorts of physical parameters, and you cannot identify a single one that you cannot identify P with this or R with a single physical parameter. It's just a ratio of parameters, or yeah, it's mostly ratios of parameters, and which one is ultimately responsible, I don't know. I can't answer that question.
If I may add something, this is Hans Engler speaking here.
Ah, yes, Hans.
Yes, hello.
Welcome back.
I was muted. These other bifurcation lines or bifurcation points would be hypothetical states of the Earth's climate system that, that Earth may or may not have ever been in. So it's really hard to tell what exactly would be the physical interpretation of such a transition, but it basically means that some other geological process drives the Earth into some other region in the PQRS, domain, and then some other phenomena happen. Maasch and Saltzman only considered a certain path in this whole system, which was indicated in some of these diagrams, and so it's hard to tell what happened there.
The choice of path is probably critical. And we've explored one particular path that transforms this two-dimensional system into a complex Ginzburg-Landau equation, miraculously. I have no idea whether that path is realistic or not, but it simplifies further, and it leads you to consider a slow passage through a half bifurcation for the Ginzburg-Landau equation, which may be a model for this. And there we're still working on it, actually. We we find that as soon as you introduce a little force, periodic forcing, which obviously exists physically because Q65 is driven by many frequencies, any of these periodic external forcings may delay the onset of stability. And in certain cases, you can even prove that it comes before the onset of stability. So that may have happened too. And it's still a topic of, well, of research at this point. What might have happened? To interpret it physically is almost impossible. But our goal is to use this model to show how things might have happened and how they could happen.
Thank you. Thank you. You answered my question. Thank you very much.
Okay.
Any other questions for Hans?
Well, I have a follow-up question then.
Oh, sure.
Okay, so are you studying this model? Are you studying the Pleistocene period? The Pleistocene? I don't know if I'm saying it correctly. Is this the period that you're kind of looking into?
This all happened. Sorry, I didn't quite hear the end of your question.
Pleistocene. So it's the Pleistocene period.
Yes.
Or are you?
Yeah, this is that.
My question.
Yeah, go ahead.
Go ahead. Go ahead.
Okay, so the Pleistocene epoch, as they call it, started 2.6 million years ago. After the Pliocene, which preceded it. During the Pliocene, nothing happened really. It was a sort of steady state. But in 2.6 million years ago, there was an event, and it has been detected by a reversal of the magnetic field in the Earth. And that is considered the onset of the Pleistocene. So then you observe the glacial cycles after that, until about 10,000 years ago. So we are now in an interglacial. So that is the period that Saltzman focused on for his model. And the glacial cycle, it didn't really happen in the Southern Hemisphere. It was typically in the Northern Hemisphere, where ice the ice crust, or whatever you want to call it, extended way down until the Midwest in the US, for example. And in Europe, you can still tell where the ice flow stopped, because that's where the debris is found. So there was this period of up and down movement of the glacials, of the glacial fields, and that is the Pleistocene. So not before, and we have no idea what will happen after. But there's a fixed period of 2.6 million years where this model functions, let's say.
Thank you.
Any others? I sort of wonder how the Earth's topography plays into this. It seems that you need the glaciers at the poles to drive these currents. And so having landmass there certainly puts a place to have glaciers. I almost wonder if on an ocean planet you could have sea ice caps that do something. I don't know.
I have no idea.
Yeah.
So I think the starting point here is there's this physical situation. Something happened over a period of 2.6 million years. It happened primarily in the Northern Hemisphere. It was ice extending and retreating. Whether it happened in the Southern Hemisphere ever, I have no idea. I'm not a geoscience person. So for a mathematician, it's a challenge to explain how could this happen? That's all. And we're having a good time doing it.
Yeah. Okay. Any other questions for? Oh yeah, James, go ahead.
Yeah, I'm just curious if you could say a little bit more about the meaning of like the deep water volume. I'm trying to understand like how that changes.
Yes, I got you. So what happens in the Northern Atlantic is the overturning circulation, which picks up all the CO2, or quite a bit of CO2 from the atmosphere. So that's why it enters into this model. There is also the deep ocean, and the deep ocean does not play a role in our analysis, really. It's the strength of the overturning circulation, which then sinks, it sinks and then follows the bottom, as it were, back to the equator. That doesn't enter into the model. It's the moment when it turns from, let's say, warm northward flowing to cold southward flowing. That is the critical moment for the CO2 uptake. What happens once the CO2 is in the ocean, in the mixing layer, the top layer, the 100 meters or so, that's well known, but it doesn't play a role in our model. So it is true that, yes, once the CO2 has been taken up by the overturning circulation, the phytoplankton blossoms, and all critters enjoy a good meal. Eventually they sink to the bottom and they stay in the deep ocean, and then, or eventually they sink to the deep ocean and then they stay at the bottom. So that's what happens. But in our model, that's beyond our concern, essentially. What happens, what is of critical importance is the take-up of atmospheric CO2 by the ocean at the overturning circulation. So that's how I view it. I'm sure there are corrections possible, but you don't want to make the model more, it is a conceptual model, so you don't want to make it more complicated. There are many ways to make it more complicated, but that's not my bag.
Thank you.
Great. Well, unless there's any other questions, we can all thank Hans, and thank you for giving our first talk of this colloquium, and I'm looking forward to seeing it. Yes, we're all clapping.
Right. Thank you.
I think there's maybe a clapping emoji somewhere, but
yes.
there we go.
That's okay.
So yes, thank you very much, Hans. That was a wonderful talk, and thanks everybody for coming, and hopefully we'll be able to see you all here next week.